Welcome to today's session. In this video, we'll dive into LeetCode problem number 845, longest mountain in array. This problem challenges us to identify the longest subarray that forms a valid mountain. We'll explore different approaches and discuss their complexities. Let's get started. In this problem, we are working with an integer array called ARR, which has a length of n. Our goal is to identify a subarray that forms a mountain. A mountain, in this context, is a subarray that meets a few specific conditions. First, the subarray must have at least 3 elements. Second, there must be an index I within the subarray such that the elements before I form a strictly increasing sequence, and the elements after I form a strictly decreasing sequence. This means the elements rise to a single peak and then fall, creating a mountain-like shape. The task is to find the length of the longest mountain in the array. If no such mountain exists, we return 0. The input is the integer array ARR, constrained to a size range of 1 to 10,000, with values between -10,000 and 10,000. The output is an integer representing the length of the longest mountain or 0 if there isn't one. For example, consider the input ARR equals 2, 1, 4, 7, 3, 2, 5. The output for this case is 5 because the longest mountain in this array is 1, 4, 7, 3, 2, which has a length of 5. This section of the array satisfies the conditions of a mountain. It starts with an increasing sequence of numbers up to the peak, which is 7, and then transitions into a decreasing sequence. On the other hand, for an input like ARR equals 2, 2, 2, the output is 0 because there is no valid mountain. The array is flat, meaning there is no strictly increasing and then decreasing sequence. Without a peak, a mountain cannot exist. Now, let's look at another example. If the input is ARR equals 0, 2, 2, 3, 2, 1, 0, the output is 4. The longest mountain here is 3, 2, 1, 0, which has a length of 4. This subarray satisfies the mountain criteria since it has a peak at 3, followed by a strictly decreasing sequence. The flat section with the repeated 2s is not part of the mountain because a valid mountain requires a continuous increase, a peak, and then a continuous decrease. This ensures that plateaus or flat areas are excluded. Additionally, the problem comes with constraints that the length of ARR can go up to 10,000, and the values in the array can range between -10,000 and 10,000, so the solution must handle such cases efficiently. Finally, there are a few edge cases to consider. For example, if the array has a length of 1 or 2, such as 1 or 1, 2, it's impossible to form a mountain, so the output should be 0. Similarly, flat or monotonic arrays, like 1, 1, 1, or 1, 2, 3, don't contain a peak and should also yield an output of 0. In cases with multiple mountains, the algorithm must correctly identify the longest one. Additionally, arrays with negative numbers, such as -3, -2, -1, -2, -3, should be handled properly. Here, the entire array forms a mountain with a length of 5. Plateaus, where there are flat sections like 1, 2, 2, 1, should not count the flat region as part of the mountain. The solution should also efficiently handle the upper limit of n equals 10,000, ensuring it performs well even for the largest inputs. To solve the problem of finding the longest mountain in an array, we need to identify subarrays that satisfy the mountain conditions, a strictly increasing sequence leading up to a peak, followed by a strictly decreasing sequence. We considered several approaches to tackle this. The first is the brute force method, where we examine every possible subarray of size 3 or more and check if it meets the mountain criteria. For valid mountains, we compute their lengths and track the maximum. However, this approach involves 3 nested iterations, one for the starting index, one for the ending index, and one to validate the mountain conditions. This results in a time complexity of O in superscript 3, making it highly inefficient for larger arrays. Another approach is the 2-pass method, which uses 2 helper arrays, up and down, to store the lengths of increasing and decreasing sequences ending at each index. A mountain is identified at any index where both up and down values are greater than 0. And the total mountain length can then be calculated as their sum plus 1. This significantly reduces the time complexity to O(n), as we only need 2 linear passes to populate the helper arrays and 1 additional pass to find the maximum mountain length. However, it uses extra space for the 2 arrays, making it less space efficient. Lastly, we considered an optimized linear scan that dynamically tracks the lengths of increasing and decreasing sequences in a single traversal, eliminating the need for extra space. This optimized single-pass approach also operates in O(n) time complexity but improves upon the two-pass method by using only O(1) space. The key to this strategy is the intuition that a mountain is defined by a peak where the element at index I satisfies the condition, the value before it is smaller, and the value after it is smaller as well. By dynamically maintaining counters for the lengths of increasing and decreasing sequences, we can measure mountain lengths and update the maximum whenever a mountain ends. If the sequence breaks at any point, we simply reset the counters to ensure accurate tracking of new potential mountains. The minimal space requirement makes this approach particularly advantageous for large datasets. Compared to the brute force method, this is exponentially faster, and while it shares the same time complexity as the two-pass approach, it is more efficient in terms of memory usage. This balance of simplicity, efficiency, and scalability is precisely why the optimized single-pass method is our chosen solution. In terms of final complexity, the optimized linear scan stands out with a time complexity of O(n) and a space complexity of O(1). This ensures the solution is not only fast but also highly space efficient. By eliminating the need for auxiliary storage, it scales well even as input sizes grow. Overall, the thorough analysis of different approaches demonstrates that the single-pass strategy provides the best balance between computational efficiency and memory usage. Its ability to dynamically adapt to the array structure while maintaining minimal resource consumption makes it the ideal choice for solving the problem of finding the longest mountain in an array. To solve the problem of finding the longest mountain in an array, we need to identify specific subarrays that meet the criteria of a mountain. A mountain consists of elements that strictly increase to form a peak, and then strictly decrease after the peak. Importantly, this mountain must have at least three elements, one part that increases, one peak, and one part that decreases. To implement an optimized solution, we start by initializing some essential variables. First, we calculate the length of the input array and store it in n. If the array length is less than 3, it's impossible to form a mountain, so we return 0 immediately. Next, we initialize max_length to 0, which will track the maximum length of any mountain we find. Finally, we set a pointer I to 1, as the first element of the array cannot be a peak. This pointer will help us traverse the array and identify potential mountains. Now we move on to traversing the array to identify mountains. We continue iterating while I is less than n1, ensuring there's room for both the left and right sides of a potential peak. To determine if I is a peak, we check the condition I1, I plus 1. This guarantees that the element at I is greater than its neighbors. If the condition is not satisfied, we simply increment I and proceed to the next element. However, if I is a peak, we then expand outward to determine the full length of the mountain. To do this, we first expand to the left to count the increasing sequence. Starting with left equals I1, we move backward as long as left 1 is less than left. Similarly, we expand to the right to count the decreasing sequence. Starting with right equals I plus 1, we increment right while right is greater than right plus 1. Once both sides are fully expanded, we calculate the mountain length as right left plus 1 and update max_length if this new mountain length is greater than the current max_length. Finally, to avoid redundant checks, we set I equals right, effectively skipping the processed mountain. The final step is to return the maximum mountain length once the traversal is complete. By the end of the iteration, max_length will hold the length of the longest mountain in the array, or 0 if no valid mountains were found. Let's summarize some key insights. First, identifying the peak is critical, and we use the condition I1, I plus 1, to ensure the element at I qualifies as a peak. Second, expanding around the peak allows us to capture the full extent of both the increasing and decreasing sequences, ensuring we account for the entire mountain. Third, skipping processed mountains by updating I to right helps optimize the traversal and prevents redundant checks. Together, these steps ensure an efficient and accurate solution to the problem. It's important to consider edge cases and the data structures used in this algorithm. For instance, arrays with fewer than 3 elements are immediately invalid since they cannot form a mountain. Similarly, arrays that are strictly increasing or strictly decreasing will not contain any peaks, and the result should be 0. Additionally, peaks located at the boundaries of the array cannot form valid mountains since they lack both an increasing and a decreasing sequence. As for the data structures, this algorithm uses integer variables such as I, left, and right to manage traversal and expansion. The max_length variable is used to track the maximum mountain length, while the input array ARR is processed directly without requiring any additional data structures. This simplicity contributes to the efficiency of the solution. The algorithm is highly efficient, with a time complexity of O(n). This is because the algorithm involves a single traversal of the array, and each mountain is processed in constant time relative to its size. By skipping processed mountains, we avoid unnecessary iterations, ensuring the traversal remains linear. The space complexity is O(1), as the algorithm only uses a constant amount of extra space for the pointer variables and does not require any additional storage or data structures. These characteristics make the solution both time-efficient and memory-efficient, suitable for handling large input arrays. Here, we begin by defining a class called solution and implementing a method named longestMountain, which takes an array, ARR, as input. The first thing we do is calculate the length of the array, n. If the array has fewer than 3 elements, we can immediately return 0, since a valid mountain requires at least 3 elements. Next, we initialize two variables, max_length, which will store the length of the longest mountain we find, and I, which is our pointer starting at index 1. The reason we start at 1 is that a mountain peak cannot exist at the very first or last position. Now, we enter a while loop that runs as long as our pointer I is between the first and last indices. Inside this loop, we check if the current element, ARR, I, is a peak. A peak is identified when the element is greater than both its left neighbor, RR, I1, and its right neighbor, RR, I+1. If this condition is true, we initialize two pointers, left and right, to 1, 1 and I+1, respectively. These pointers will help us expand outward from the peak to find the full extent of the mountain. The left pointer moves backward as long as the previous element is smaller than the current one, indicating that we are on the upward slope of the mountain. Similarly, the right pointer moves forward as long as the next element is smaller than the current one, marking the downward slope of the mountain. Once the left and right pointers have fully expanded, we calculate the length of the mountain as right, left +1 and update max_length if this new length is greater than the current maximum. After calculating the length of the mountain, we move the pointer I directly to the right boundary of the current mountain. This allows us to skip redundant checks for elements that are already part of the mountain, optimizing our traversal of the array. If the current element is not a peak, we simply increment I by 1 to continue checking the next element. Finally, once the while loop has completed, meaning we've traversed the entire array, we return max_length. This value represents the length of the longest mountain in the array. By using this approach, we ensure that we efficiently identify and measure all potential mountains, skipping unnecessary checks and operating within O(n) time complexity. Here, we are implementing a solution to find the longest mountain in an array, where a mountain is defined as a subarray that strictly increases to a peak and then strictly decreases. First, we start by checking if the array length is less than 3, as it's impossible to have a mountain in such a case. If the condition is met, we return 0 immediately. Next, we initialize maxLength to keep track of the longest mountain found in a pointer I starting at 1, as the first and last elements cannot be peaks. Then, we enter a while loop that runs until I reaches the second to last element. Within the loop, we check if the current element is a peak by ensuring it is greater than its neighbors. If this condition is true, we initialize two pointers, left and right, to expand outward from the peak. The left pointer moves backward to find the start of the mountain by checking if the elements continue to decrease as we move left. Similarly, the right pointer moves forward to identify where the mountain ends by ensuring the elements decrease as we move right. Once we have identified the boundaries of the mountain, we calculate its length by finding the difference between the right and left pointers and adding 1. We then compare this length with maxLength and update maxLength if the current mountain is longer. To avoid redundant checks, we move I to the position of the right pointer, which marks the end of the current mountain. If the current element is not a peak, we simply increment I to continue scanning the array. After the loop completes, we return maxLength, which holds the length of the longest mountain in the array. This ensures that our implementation is efficient and avoids unnecessary computations while adhering to the problem's requirements. Here, we start with a basic example where the input array is 2, 1, 4, 7, 3, 2, 5. The goal is to find the length of the longest mountain. First, we initialize the variables. The length of the array n is 7, max_length is set to 0, and we start iterating from index I equals 1. In the first iteration, the values are ARR I1 equals 2, ARR I equals 1, and ARR I plus 1 equals 4. Since this does not satisfy the peak condition ARR I1, ARR I plus 1, we move the pointer to the next index. In the second iteration, ARR I1 equals 1, ARR I equals 4, and ARR I plus 1 equals 7. Once again, this is not a peak because the condition is not met. So, we increment I to 3 and proceed to the next step. Now, at the third iteration, the values are ARR I1 equals 4, ARR I equals 7, and ARR I plus 1 equals 3. This time, the condition for a peak, ARR I1, ARR I plus 1, is satisfied, so we identify 7 as a peak and begin expanding outward to find the full mountain. First, we expand to the left starting from left equals 2. We check if ARR 1, ARR 2, 1 less than 4, which is true, so we decrement left to 1. Then, we check ARR 0, ARR 1, 2 less than 1, which is false, so we stop expanding left. Next, we expand to the right starting from right equals 4. We check if ARR 4, ARR 5, 3 greater than 2, which is true, so we increment right to 5. Then, we check ARR 5, ARR 6, 2 greater than 5, which is false, so we stop expanding right. The total mountain length is calculated as right left plus 1 is equal to 5, 1 plus 1 equals 5, and we update max_length to the maximum of the current max_length and this mountain length, which is 5. Finally, we move I to right equals 5 to continue checking the array. In the fourth iteration, the values are ARR I1 equals 3, ARR I equals 2, and ARR I plus 1 equals 5. Since this does not form a peak, we increment I to 6. At this point, the loop ends, and the final maximum mountain length is 5. The output for this example is 5. In this example, the input array is 2, 2, 2, and we want to determine if there are any mountains. First, we initialize the variables. The array length n is 3, max_length is 0, and the starting index I is 1. In the first and only iteration, the values are ARR I1 equals 2, ARR I equals 2, and ARR I plus 1 equals 2. The peak condition ARR I1, ARR I plus 1 is not satisfied because all the elements are equal. Therefore, we increment I to 2. Since there are no more elements to check, the loop ends. As no peaks were found, the final maximum mountain length remains 0, and the output for this example is 0. For this example, the input array is 1, 2, 3, 4, 3, 2, 1, where the entire array forms a mountain. First, we initialize the variables. The array length n is 7, max_length is 0, and the starting index I is 1. In the first iteration, the values are ARR I1 equals 1, ARR I equals 2, and ARR I plus 1 equals 3. Since this does not satisfy the peak condition, we increment I to 2. In the second iteration, the values are ARR I1 equals 2, ARR I equals 3, and ARR I plus 1 equals 4. Once again, this is not a peak, so we increment I to 3 and proceed to evaluate the next set of values. At the third iteration, the values are ARR I1 equals 3, ARR I equals 4, and ARR I plus 1 equals 3. This satisfies the peak condition ARR I1, ARR I plus 1, so we identify 4 as the peak and begin expanding outward. First, we expand to the left starting from left equals 2. We check if ARR 1, ARR 2, 2 less than 3, which is true, so we decrement left to 1. Then, we check ARR 0, ARR 1, 1 less than 2, which is also true, so we decrement left to 0. At this point, we cannot go further left. Next, we expand to the right starting from right equals 4. We check if ARR 4, ARR 5, 3 greater than 2, which is true, so we increment right to 5. Then, we check ARR 5, ARR 6, 2 greater than 1, which is also true, so we increment right to 6. At this point, we cannot go further right. The total mountain length is calculated as right left plus 1 is equal to 6, 0 plus 1 equals 7, and we update max underscore length to the maximum of the current max underscore length and this mountain length, which is 7. Since there are no more elements to check, the loop ends, and the final maximum mountain length is 7. The output for this example is 7. To analyze the time complexity of the algorithm, we start by looking at the outer loop, which iterates through the array using the pointer I. Unlike a typical loop, I doesn't always increment by 1, instead, it jumps to the end of the current mountain whenever a peak is identified. This ensures that no element is revisited unnecessarily. At most, each element is processed twice, once during the expansion of the left pointer and once during the expansion of the right. This means that the total number of iterations for the outer loop is directly proportional to the size of the array, n. Next, the inner loops come into play. When a peak is found, the left pointer moves backward and the right pointer moves forward to determine the boundaries of the mountain. Each element is visited once during this process. Combining the behavior of both the outer and inner loops, we can conclude that each element is processed at most twice, resulting in an overall time complexity of O(n). Now, let's evaluate the space complexity of the algorithm. The memory usage is determined by the additional variables used during execution. Here, we only have a few variables, such as I, left, right, and max underscore length, which all take up constant space. Importantly, the amount of memory these variables require does not grow with the size of the input. Additionally, the input array itself is provided as part of the problem, so it doesn't contribute to extra space usage. Since the algorithm doesn't rely on any additional data structures or recursion, the overall space complexity is constant, or O(1). Now let's look at the best, average, and worst-case scenarios for the algorithm. In the best case, if the input array has fewer than 3 elements, the algorithm immediately returns 0 without any additional processing. This takes constant time, or O(1). In the average case, for an array with multiple peaks and valleys, the algorithm ensures that each element is processed at most twice, once by the outer loop and once during the inner expansion loops. This keeps the time complexity at O(n). In the worst case, where the entire array forms a single mountain, the algorithm will still only process each element twice, once for the left expansion and once for the right. Even here, the time complexity remains O(n). To put this into perspective, a brute force approach would examine all possible subarrays to check if each one forms a valid mountain. That would require 2 nested loops, resulting in a much higher time complexity of O(n squared). By contrast, the given solution avoids this inefficiency, achieving an optimal O(n) time complexity through a single pass and 2-pointer expansion. Finally, let's confirm the time complexity mathematically. For an input array of size n, the worst-case scenario occurs when each element is visited twice, once by the left pointer during backward expansion and once by the right pointer during forward expansion. This means the total number of operations is proportional to 2n, which simplifies to O(n). On the space side, the algorithm uses a constant amount of memory regardless of the input size, leading to a space complexity of O(1). To summarize, the algorithm achieves an optimal time complexity of O(n) and a space complexity of O(1), making it highly efficient for solving this problem. When solving the longest mountain in array problem, there are some common mistakes to watch out for. First, misidentifying the peak of the mountain is a frequent issue. The peak must have strictly increasing elements to its left and strictly decreasing elements to its right. If this condition isn't met, it isn't a valid mountain, and including such peaks will lead to incorrect results. Secondly, it's important to avoid including flat sections of the array, those where values remain constant, as part of the mountain. A valid mountain requires strict changes in elevation, so any flat sections break the increasing or decreasing slope requirement. Another mistake is counting overlapping mountains as part of the same structure. Each mountain must be treated as distinct, and overlapping sections should be separated to prevent inflated lengths. Finally, boundary conditions often get overlooked. Mountains cannot have their peaks at the boundaries of the array because a valid mountain requires slopes on both sides. Ignoring this can lead to invalid mountains being counted, which skews the solution. Another common pitfall is relying on inefficient approaches like brute force, which checks every possible subarray. This can result in an n-cubed time complexity, making it infeasible for larger arrays, such as those with tens of thousands of elements. Instead, understanding the key pattern of a mountain is essential. It consists of three distinct parts: an increasing slope, a peak, and a decreasing slope. With this structure in mind, you can implement more efficient solutions. For instance, a two-pass or single-pass technique allows you to calculate the slopes efficiently, reducing the complexity to n. Additionally, always consider edge cases, such as arrays that are too short to form a mountain, those with fewer than 3 elements, or arrays that are strictly increasing or decreasing, which don't contain any valid mountains. It's also important to explain the trade-offs involved in your approach during interviews. For example, you should be able to justify why a two-pass method is preferred over brute force, citing its significantly better time complexity. This problem is closely related to several other LeetCode challenges, and understanding these can deepen your grasp of the concepts. For example, in LeetCode 162, Find Peak Element, the goal is to identify a peak in a 1D array, which involves similar logic for detecting local maxima. LeetCode 941, Valid Mountain Array, is a simpler version of this problem, where you verify if the entire array forms a valid mountain instead of finding the longest one. Then there's LeetCode 852, Peak Index in a Mountain Array, which focuses solely on detecting the peak index in a given mountain array. Lastly, LeetCode 376, Wiggle Subsequence, explores alternating increasing and decreasing patterns, which can help you understand related concepts like transitions and slopes. Familiarity with these problems can give you a broader perspective and help you recognize patterns that are useful in solving the longest mountain in array challenge. There are several approaches you can use to solve this problem, each with its own trade-offs. The two-pass approach involves using two arrays to store the lengths of the increasing and decreasing slopes for each index. After calculating these, you can iterate through the array to find the maximum mountain length. This method is efficient in terms of time, with n complexity, but requires additional space, also n, for the slope arrays. Alternatively, the single-pass approach dynamically calculates the slopes while traversing the array just once. This method is more space-efficient, requiring only 1 additional space, but implementing it correctly can be more challenging. Finally, there's the brute force approach, which checks all possible subarrays to see if they form a mountain. While this method is conceptually simple, it's highly inefficient with n-cubed time complexity, making it impractical for large inputs. Choosing the right approach depends on the problem constraints and your ability to balance time and space efficiency. Great job! Today, we tackled longest mountain in array, breaking it down step by step. Remember the importance of identifying patterns in arrays and optimizing your approach for efficiency. Thanks for joining, and don't forget to like and subscribe for more problem-solving strategies. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!